Hi, in this video, I'll be going through an introductory course into group theory, and in the previous video, we've defined what is a group. So now we shall do what is known as a subgroup, and a subgroup is a subset of a group is a subgroup if and only if it is non-empty and is closed under the products of under products and inverses. And this really just says that the operation, the binary operation restricted to H is still a binary operation on H. And H has the properties of a group. And if it's a subgroup, we can write this notation. So, in essence, subgroups are just subsets of groups which are themselves groups. And when we say H is a subgroup of G, we always mean that the operation for G and H is the operation of G restricted to H. So they are like the same operation. So the cancellation laws imply that the identity of H must be the same as the identity of G, and that the inverse in H is the same as the inverse in G. So, and that's really because the inverse and identity are unique. So even when you restrict them to a smaller set, and because they must still be in groups, they must equal to each other. So certain things that are subgroups is that the integers is a subgroup of rationals, and the rationals are a subgroup of reals under the operation of addition. And the trivial subgroup, of course, is just having one, and G itself is a group. So if H is a subgroup of G and K is a subgroup of H, then K must also be a subgroup of G. And that's quite obvious to see based on this definition itself. So what we want is now a criterion to prove something is a subgroup easily, instead of always checking the three axioms. So we say that it's a subgroup if and only if it is non-empty and X times Y inverse is the element of H. So if H is a subgroup, then certainly 1 and 2 will hold, because H contains the identity and its inverse of each element, and hence H is closed under multiplication as well. So if it's a subgroup, then these properties hold easily seen. Now with these properties, you want to prove that it is a group, so it must satisfy 1 and 2 and 3. 3 is obvious because the inverse is over here. Now you must satisfy number 1, so you want to prove you let y equals to x and apply the property to deduce that x times x inverse, which is 1, it lies in H. So H contains the identity for every element. Then again, by 2, H contains 1 in X, and so H contains the element, the inverse. And if you take 2 elements, then of course you're going to be closed under multiplication as well. So H is in fact a subgroup of G. And if you are finite, then you only need to show that you're closed under multiplication, because you're automatically closed under inverse. Because your inverse must be back to the same set over here. So you can't like expand, keep on expanding. Next, we shall go through what is known as a cyclic group. And a cyclic group is basically a group that is generated by a single element. And the notation is usually like this. So we say A generates the group G. So what is this notation supposed to mean? It is all the elements of the form xn where n runs through all integers, meaning it's x0, x1, x2 all the way, union with x minus 1, x minus 2 all the way. And so what does this mean is that you collect all the elements where 1, then you use the operation star to get with x, so this becomes x. Then now you start to get x squared and so on. So you collect all those elements inside, and we say that this generates a subgroup. And we can actually check that this subgroup is, this group that we generated is actually a subset of G. So it is possible that a cyclic group has more than one generator, because if H equals to the cyclic group generator by X, it is also equal to the cyclic group generator by the inverse, because this set property is the same. And what to note is that it is not true that all powers of X is distinct. And one simple example is the finite group of 0 and 1. When you take 1 plus 1, it equals to 2, which equals to 0. So you get going back to here. And 1 plus 1 plus 1 4 times will also be 0. So I hope you're clear on what's a subgroup. More examples will be like Z modulo 8 and the multiplication operation. And then a cyclic subgroup will be just generated by 1. So it's either the trivial group. If it's generated by 3, then it's 1 3. If it's generated by 5, it's 1 5. If generated by 7, it's 1 7. And since G itself is not equals to any of these subgroups, cyclic subgroups, then G itself is not cyclic. But what we shall prove now is that every subgroup of a cyclic group is cyclic. And so to prove this, we just take G to be a cyclic group. So let's just say generated by A. If H is a trivial group, then is obviously cyclic. And if H is not 1, then there exists an element in G that lies in H. So we call this AR. Then we can collect all these elements and find the smallest one. And there must exist a minimal due to the well-ordering principle. And so this minimal means that A to the power of K, the generator, must be a subset of H. And now you suppose there is a proper subset, then there exists a H not in this in big H minus away, complement away the cyclic group created by AK. So because H is also in G, then it equals to AT for some T. But not being in H means that K doesn't divide T. So this means that T equals to M times K plus N, where N is some remainder that lies in between 0 to K. Then you find A to the power N, and we realize that A to the power N is going to equals to A to the power T times A to the power M K. And then this is the element of H, which contradicts the minimality of AK being the minimal element in S. So this contradiction means that AK must equals to H, and this shows that H is cyclic, and any subgroup must be cyclic. And so we're done. And then now we define what is known as the order, and the order is defined to be the power of n such as x to the power n equals to 1, meaning you do the operation n times, then it equals back to the identity. In this case, x will be said to be order of n, and the order of a group is just determined by the number of elements. So there is an actual difference between order of group and order of an element. So you can see that the powers of these elements of 2, 4 and 8 is of the powers of the element 2 are 2, 4, and 8 equals to 1. And the identity in this group, so 2 has the order of 3. And similarly, 3 has the order of 6. Since 3 to the power of 6 is congruent to 1 mod 7. Next, we shall prove that if H is a finite cyclic group, then the order of H equals to the order of an element. So this means that if H is finite, then x to the power n must equals to 1. And these are the distinct elements in H. So the cyclic group equals to 1, x, and all the way to x to the power n minus 1. And if it's infinite, then xn will never equals to 1. And for all ab, xa to the power ab cannot equals to x to the power b. And this is really just saying that your group operation is distinct. So we shall first prove the first property, and that is just saying that the order of x equals to n, and n is finite. So the elements are all distinct because x to the power a, xa equals to xb, then x b minus a must equals to x0, which equals to 1. And this contradicts n being the smallest positive power of x identity, giving the identity. Thus, H must have at least n elements, and it remains to show that these are all of them. So you can do the usual trick of the division algorithm, and you get the following as desired. So I'll leave it to you to read the proof, as it's quite straightforward. So what you now need to know is that if you are a cyclic group, then your order of one generator is equal to the order of the entire the number of elements in a finite cyclic group. And that really show why you can think of the order of an element to be an order of a cyclic group. And lastly, I'll leave it to you, and I've given you guys the breakdown of the proof to read through proposition 3 and 5, which are relatively straightforward. And I'll just say some things to note is that what we want to achieve from doing proposition 3 is that if you know that x to the power m equals to 1 and the order of x is n, then we know that n must divide m. So the order of the element divides x to the power m, divides m. And then what we want to say is we want to now know the order of x to the power a, and that's really just x to the power of n, n divided by the GCD of n and a. And I'll leave it to you to check the details. And with that, we shall now see that H being, if H is a finite cyclic group, then H equals to x power n, the cyclic group of generated by x power n, if and only if the GCD of a and n equals to 1. And this really shows that the generators of H, the number of generators, is the Euler-Tortillon function, which we'll go through in group theory part 5. So in part 2, we see that the order of x equals to n, which is finite, and by an earlier proposition, we know that x to the power a generates a subgroup of H of order x to the power a, and this subgroup equals all of H if and only if the orders are equal. And so the orders are equal if and only if n divided by the GC of a to n equals to n. And this really means that the GCD of A and N equals to 1. And so we are done. And this, by the definition of the Euler-Tothean function, the number of elements in 1 to n such that they are co-prime. And so these are indeed the generators of H, because you only collect the number of the elements that are co-prime to be the generators of H. And so that's all. I hope this gives you an intro to subgroups, and a type of subgroups is known as the cyclic groups, and you can see there are many propositions in the textbook for you to try out to better understand what is a cyclic group. That's all for this video. I hope you have enjoyed it. I'll see you in the next video. Bye.